Okay, so the first thing I'm going to review is on open and closed sets. Okay, so this was one of the first things from this section that we talked about. So I'm going to draw it like this with like a picture. Okay, so if I have a dotted line is going to represent an open set. Okay, so an open set means that if I pick a point inside of the set, I can draw a circle around it that is entirely contained in my set. Okay, I might have to make this circle very, very small, but at some point I can make a circle small enough to be fully contained inside of my set. Okay, this doesn't work if I have something with a boundary, something like this, because if I pick a point on the edge and I draw a circle around it, no matter how small that circle is, it's going to be it's not going to be contained within the square, right? There's always going to be a little bit that's outside of the square, no matter how small that is. Okay, so this is what an open set is. An open set, I can pick a point and always draw a circle inside of it. The easy way to think about it is that it has no boundary. Okay, so the whole boundary is kind of just not there. Whereas this one, right, it all has a boundary. So there's no boundary at all. Here there's a boundary around the entire thing. Okay. Um, so if I had a set that, again, something like this, but maybe included these points, right? So these points were actually in my set. So these ones here, but not the rest of them, and all this. Okay. This would not be an open set. Okay, because if I pick a point here on the boundary and I draw a circle around it, um, it would never be fully contained inside of my set. So yeah, you can think of an open set. You can think of an open set as a set with no boundary. A closed set is kind of the opposite of that. A closed set has a boundary around the entire thing. Okay, so for example, this is a closed set. So this is an open set. This is a closed set. So a closed set is different. Basically, what it technically means is that if I take a limit of, or if I take a sequence of points in this set, it doesn't matter what sequence, and I do the limit, it's always going to be the limit is also going to be in the set. So if I do a limit getting closer and closer and closer to the boundary, the limit converges to a point in my set. Okay, so how is this different from an open set? So here's an example of an open set. Let's do the open interval from 0 to 1. So here in this case, when I say I can draw a circle around it. It's a 1D thing, so it's just going to be like this open interval. But if I do a limit going towards 0, right? All of these points, if I go closer and closer to 0, all of these points are in my set. They're all in the interval, but the limit of them, 0, is not in my set. Okay, a closed set, right? So now if I do a limit of points going to 0, right? All of these points are in my set, and if I do the limit of those points, then I get 0, which is in my set. Oh my gosh. Okay, so let me just draw this distinction that these are very different types of sets. It seems like a very trivial thing, right? I just added the endpoints. What's the big deal? So let's think of this. If I have an open set like this, actually, do a closed set. If I have a closed set like this, and I look at a function like this, okay, the maximum of this function is going to be over here at this point, right? This is going to be the max, and the minimum is going to be over here at this endpoint here. Okay, so this function, it actually has a maximum value and a minimum value on this set. Okay, that seems obvious. How would that change? If I have an open set where I don't include the endpoints, and I have this same thing. So now I don't have these endpoints. Okay, now this function actually doesn't have a maximum value over this interval, right? Because we can get closer and closer to this value, but we never actually get to that value. Okay, so there is no biggest value, right? There's no maximum. Um, so that's interesting, right? So that's a big difference between having a maximum minimum value on a closed set and not having a maximum minimum value on a open set. Okay, so for us, these are actually going to be really easy to distinguish. If it's open, closed, both, or neither. Okay, so it can be any one of those. There's examples where it's both. There's examples where it's neither. Um, page. So for example, if I have a set that looks like this, so dotted means that that's not in the set. Something like this would be neither. It is not open, right? Because I take a point on this edge of the boundary, a point here, and that circle is always it's never going to be contained fully inside of the set. But it's also not closed because if I do a limit of points going this way, right, it converges to something that's not in the set. So it's not open and it's not closed. So it's neither. Okay. Um, Here's an example where it's both, is the entire real number line. The entire real number line, let me do it this way. Open. Do you have a little pointer? Sorry, kind of hard to see my cursor. I don't. I will get one for next time. I can kind of see your drawing dots, but it's weird. Okay, yeah, I'll get a highlighter for next time. I can also make this a little bit bigger. Okay, so here, if I'm just doing an open and, or if I'm just doing the entire real number line, right? If I pick a point, I can always draw an interval around it and it's fully contained inside of the real number line, right? Because it contains everything, right? So I can always do this, right? Because it doesn't matter which interval I pick around it, it's still contained inside my set. So it's open, right? It has all of these all of these open intervals around it. But also, if I do a limit of points, right? If I take a limit, I'm never going to converge to something that's not in my set. So it's also closed. So it's possible to be open and closed. Um, you probably won't see examples like that, but just know that it's definitely possible. Okay. What about... Okay, so to get some more examples, let's go ahead and move to the next section, and we'll use some of those questions as examples about open and closed sets. So this is domain and range. Okay, so the domain is the set of all valid inputs to a function. Okay, so let's find an example. Let's do this one, x over yz. So f of x, y, z equals x over y times z. Okay, so I want to figure out what are the inputs that I'm not allowed to put in to this. Okay, so here I look at when is this undefined. It's undefined when z is 0 or when y is 0. Okay, but really that's the only restrictions that I have. So those points are not going to be in the domain. Okay, so the domain is going to be the set of all x, y, z such that y is not 0 and z is not 0. Okay, so these are the conditions that I have to have so that this is always defined. I don't have any undefined points. If I have... Oh, and what is the range? So let's just, for example, so the range is the set of all possible outputs from this function. Okay, what are all of the possible outputs I can get from this function? Well, if I pick f of x 1 and 1, right, that's just going to be x. Right, so x can be, anything, any number from minus infinity to infinity. So the range is going to be the set of all values, I'll just put it as an interval, all values in the interval minus infinity to infinity, right? Because any value that I want from this function, I can just set that value to x and y and z to be 1, and I can get that value from this function. Okay, so let's take this set here and combine this as an example for the previous set. Is this open or closed? Okay. Open, closed, both, or neither? What do you guys think? Okay, I'm hearing open. Looks like most people are saying open. Okay. So what does this look like? Let's see, is it going to be open? what is this? So let's just look at what it would be in 2D, right? So I'm going to look at this. So this is my x-axis and y-axis, right? And z is going to be coming out this way. So y can't be 0. So it's going to be all of this and all of this on this side. And it's not going to include the y-axis. Okay? And it's also not going to include the z-axis. Right. So yes, it's going to be open. That is correct. But let's also check that it's not closed. So, because it could be both, right? So how could it be both? Um, so can I find a limit of points, a sequence of points that converges to something that is not in my set? Okay, well, if I take a limit of points going towards 0, or sorry, towards y equals 0, towards x equals 0, hold on, this is, sorry, I drew this backwards. The line y is not 0. The line y equals 0 is here, and the x-axis, the y-axis, is the line x equals 0 that is in the set. I just drew it backwards. Doesn't change anything. Okay, if I do a sequence of points going towards y equals 0, then it converges to y equals 0, which is not in our set. So I found a sequence that converges to something that's not in my set. So that means that this is not a closed set. Okay, so it's just open. Okay, good. Um, let's look at another example. So f of xy equals ln of xy minus 1. Okay, so this is, when is this undefined? So we know that whatever this is, it cannot be less than or equal to 0. So this has to be greater than 0, right? Otherwise natural log is not defined. Okay, so what does that mean? It means that if x y minus 1 is bigger than 0, it means that x times y is bigger than 1. Okay, so this is the condition I need. This is the condition that I need in order for this function to be defined. So my domain is going to be the set of all pairs xy such that x times y is bigger than 1. Okay. And the domain, well, this is just natural log. What does natural log look like? It looks like this. Okay, so is it possible to get all of these values out of this function for this domain? Right, so the minimum value, I could have x, y, I could have that getting really close to 1. So when xy is 1, this thing is very close to 0, so I'm going off to minus infinity. So I can get each of these values. I can get each of these values out of the function. I can pick x and y to get that. And then I can also make x, y, I can make that product get really big, meaning that I can go way over this way and have values that, and have the corresponding values. So when x and y are close to 1, what I mean is that, so x and y are close to 1, that's going to be this. So I can get this value, this value, this value, all of these outputs, right? So all of these are going to be in my set, right, all the way down to minus infinity. And then same thing, when x and y get really big, all of these values are also going to be in my set. Okay, so that means all of these are also going to be in the range. Okay, so the range again is going to be the set of all possible outputs, and I can get every possible number out of this function. Okay, so let's look at the domain. Let's do this again. What do you guys think? Open, closed, both, or neither? Okay. So it looks like we have a pretty good number of people saying open. Also looks like we have half the people not answering. Okay. Okay, so looks like we're going to guess that it's open. So let's see if we can show that it's open and also that it's not closed. So what does this actually look like? So we know that xy has to be bigger than 1. Or so if xy is bigger than 1, it means, so assume that x is positive for a second. If x is positive, that means that y is bigger than 1 over x. But if x is negative, I'm dividing by a negative number, so I have to flip the sign. So this is less than 1 over x if x is less than 0. So the graph of 1 over x looks like this. I'm going to draw it in a dotted line. All right, so that's the graph of 1 over x. And the region that I'm interested in, so it's bigger than 1 over x if x is positive, so that's this region. And less than 1 over x if x is negative, that's going to be this region. And yeah, that doesn't really have a boundary, right? If I pick any point actually in the set, right, I can zoom in close enough and draw a circle around it. That's fully contained inside my set. There's no boundary here. And it goes off to infinity in the other direction, so that's fine. So yes, this is open. For sure it's open. Now, is it closed? Can I find a limit of a sequence of points that converges to something that's not in my set? Well, if I just do if I take the sequence xn equals 1 plus 1 over n and y equals 1, yn equals 1. Okay, so this sequence, as n goes to infinity, it converges to 1. Or the product of these. So the product, x and yn. So the limit, as n goes to infinity, that's just going to be 1. So this limit converges to something that's not in my set, meaning that it's not closed. So it's only open. Okay. Let's do one last one on this. So f of xy is the tangent of x minus y. Okay, so what is the domain of tangent? So just as a regular function, the domain of tangent, I can take the tangent of not any, let's see. So I can't take the tangent of pi over 2, because that would be infinite. Okay, or multiples, so pi over 2 or minus pi over 2. So I know that this, whatever it is it can't equal k pi over 2 with k odd. Because that's what the domain is. So here, let's just assume that we're only, no, let's just leave it like this. Okay, so I know that x minus y is not equal to, or yeah, is not equal to k pi over 2, right? So this is the condition for things that are not in the domain, okay? Oh, sorry, no. This is the condition that it is in the domain. It has to not be equal to this. So let me just solve for this. So I have that y is not equal to x minus k pi over 2. Okay, so the domain, it's just restating the same condition. All the pairs xy such that x minus y is not equal to k pi over 2 for some odd value of k. All right. So is this an open or closed set? Oh, come on. What do y'all think? So I'm going to start sketching out what this set looks like. So here I know that it's all of the points that are not, so I can't have x minus pi over 2. Do I want to sketch this? Actually, check this out. Let's see if this works. Equals wolf set is it going to do it? Okay. I guess it's not going to plot it for us. Or will it? No, it's not going to plot it for us. Okay, yeah, it's going to be open. Specifically, it's not going to be closed because, if I just pick y equals 0, if I pick y equals 0, then I could do a sequence of points xn that go closer and closer to pi over 2. Right? I could have these being inside of my set, but the limit would not be. So this is not closed. And is it open? I'm going to say yes, it is. How would I draw this? So the line, Okay, so, oh, I see. So basically this is going to look like a bunch of um, lines like this. Okay, and then my set is everything inside of these. Okay, so let's trash that because that didn't work. Okay, so any more questions on, or any questions on domain and range and stuff? I think I was pretty thorough on those. So real quick, let me get to Clayton's question on what's the difference between, uh, what is the difference between df, dy, dx, and df, dx, dy. So here, what this means is if I want to take the derivative, so f is a function of x and y, and I say I want to take the derivative of f. Okay, your first question should be which derivative or in what direction, because I can't really just talk about the derivative. There's more than one. Okay, so I could talk about let's just say I talk about the x derivative, or I could talk about the y derivative. Okay. Now, if I said I want the second derivative, okay, so that's the derivative of the derivative. So the second derivative, I could do the derivative of the x derivative. Oh, sorry. I thought I said, oh, I see, I see. Yeah, yeah, okay. Sorry about that. Okay, so I could do the derivative of the x derivative, or I could do the derivative of the y derivative. So if I'm doing the derivative of the x derivative, I have to ask the same question. Which one am I doing? Um, I could do the x derivative of the x derivative. I could do the x derivative, sorry, the y derivative of the x derivative. Or over here for the y derivative, I could do the x derivative of the y derivative. And then my other option is I could do the y derivative of the y derivative. Okay, so our notation for this is that this is going to be d squared f dx squared. This one is going to be d squared f dy dx. So this means the y derivative of the x derivative. This is going to be d squared f dx dy. So the x derivative of the y derivative. And then finally d squared f dy squared. And of course, if I have like a third variable or fourth variable, I could also have those, they call these mixed derivatives. I could have those as well. So that's what the difference is, right? This is the y derivative of the x derivative, and this is the x derivative of the y derivative. Now, one fact is that if your function is differentiable, then these two things are going to be equal. Right? It doesn't matter which order I do the derivatives in. Okay, so as far as the actual difference, it doesn't matter which way you compute them, right? They're going to be the same thing. Okay, but as far as what they represent, that's what they represent, right? The y derivative of the x derivative and the x derivative of the y derivative. Okay, so if this is not true, then either your function doesn't exist or it's not differentiable. Okay, so this is related to the asking if a um, asking if a function is a gradient of something. Basically, what you end up showing is that this function doesn't exist. Okay, I'm gonna stop the recording here real quick.